So we're going to look at discrete probability distribution tables. These are simply just a way of showcasing all the probabilities on offer. Now, most of our discrete probability distribution tables won't have this bottom line. That's one that I've added in, but we'll leave that for now. What do we think, looking at those top two columns, this might represent? What's this situation?
Dice.
Rolling a dice. Okay, that's a discrete probability distribution because we can only roll a 1, 2, 3, 4, 5 or 6, correct? And because I'm not playing at Jacob's Casino, the odds are equally likely. This isn't a rigged game. Every opportunity, every face of the dice has equal opportunity at rocking up. Now, they give you this funky equation for expected value. Does anyone know another name for expected value or a word that you might be familiar with? Some people call me this. Taylor Swift sung a song about it.
Shake it off.
No, not quite. Showing Will's knowledge of Taylor Swift though. Why you gotta be so... I just think it's funny that Taylor Swift sings a song about being average when her music is, no, mean, okay? So mean and expected value are very similar concepts. So if I was to roll these dice 100 times, what would be the expected value for the average roll? What would be my expected value if I rolled it 100 times? What would I expect to get per roll? So if I was to add up all these scores and I was to roll it 100 times and then divided my answer by 100, what would I expect to see? I'd expect to get 100 ones in a row. If I was to roll my dice 100 times, what would be the average or the expected score for my roll? 3.5, correct? And I get that by multiplying each value by its probability. So 1 times 1 on 6, 2 times, you get the idea. So that's what this equation means. It's the addition, the sum of my x value multiplied by my p value. So I just do that one, plus 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 that one. Happy with that? And then we get a score of 3.5, which happens to lie half in between our values. Why would we expect that? Because they're all same probability and they're all one away from each other. Sweet. So we would expect our mean to fall in the middle of our data here. Is that always going to be the case, Buck?
No.
How do we expect to see that change? If the probability is different, so say the probability, let's say the example before with the shooting, we wouldn't expect the probability of that to be the same across the board. What about with if the scores were different? Yeah. Okay, so if you're looking at a basketball context, for example, and 2 and 3 points, then you might find that you get a different distribution. So just be aware of that, but as long as you remember that formula, you'll be right, it is on your formula sheet. So if we think of expected value a little bit like mean, the next concept we need to look at is variance. What do we think variance is talking about?
How much it varies.
What would you expect what do you think I mean when I say William's responses in my class have a high coefficient of variance or a high amount of variance? What is that telling you?
They are very different.
They're very different, there's a high amount of variety. Are they all centered around a similar spot? Like are all these questions and answers good?
Yes.
That's what Will might think, but when we who understand the English language you're engaging in, we know that means that there's a lot of unpredictability in our results. So in the questions and the things that he says, there's a lot of unpredictability. Will you expect this data to have high variance or low variance? High variance, because all the values are equally likely. If I was, for example, playing, let's try and think of something with, if I was to look at the median, high variance, low variance, sorry.
Wait, is high variance good or bad?
High variance is less predictable.
Less predictable.
Yeah. So like I can't, if I'm doing something like looking at scores of year 11 methods or year 12 method students in this class, and I had a class that had everyone getting like 11s and 12s. Everyone in the class got 11s and 12s. That would have a very low variance because all your values are similar. Let's say I'm teaching in the same class and I've got some kids sitting on 15, some are on 1, some are on 14, some are on 2. That's got a high amount of variance. There's a big spread of data. Does that make sense?
Wait, so what's this one?
This has got high variance because all my values are equally likely. So think about the example where I had a class full of kids getting 11 and 12. The likelihood of a student getting an 11 in that class is very high. Make sense? Whereas in the class where I've got everyone, I've got some 15s, I've got some 1s, I've got some 14s, I've got some 2s, the chance of getting an 11 is about the same as getting a 1 or a 15.
Okay.
Cool?
Yeah.
So that's a high amount of variance. And the way that we calculate that is using, this is the formula we see on our formula sheet, and that is just the probability multiplied by x minus the mean squared. So it'd be 1 minus 3.5 squared times my probability. 2 minus 3.5 squared times my probability. Why do I need to square that? If I didn't square it, I'd get negative values the whole way across, correct? If I didn't square that, my value would be 0 here. Sweet. Another representation of this, and this is why we put this value in here, that's another representation of the same formula. I'll just check that I've got that the right way around in my order. Actually, I was supposed to that, but someone stole my text.
Page.
Can you confirm that to me, Paige? Is it ex squared minus ex squared, or the other way around? In 8.1. Read the front, see if you can find it. Whilst Paige is doing that, what we do with this table now is we square these values. So it should be 1, 4, 9, 16, 25, 36. So to find ex squared, so instead of, which way is it, Paige? Which one goes first?
The other one.
Other one, so I've got it the wrong way around.
Yes, you did.
So it is ex squared. Why did it in red so we could figure that out? So then what we do is we find our expected value the same way when we use the bottom row, minus 3.5 squared. So what I want you to do is try and figure that out now, and I'll give you 2 minutes to determine the variance of that and see how you go comparing it to mine.